those of you on Zoom, can you hear me?
Yeah.
Yes.
Yeah.
Good. Okay, go ahead and mute your microphones for now. I want to share my screen. Mouse is sticking. As soon as I can get it. There we go. Okay, so I'm going to turn to Canvas. Usually I would distribute printed syllabus, but this time I'm posting the syllabus on Canvas. And we'll spend a few minutes going over the syllabus. Can you hear me in the back? Okay. All right. Okay, so if you open up Canvas, under the item called Files, under Files, okay, I've got the syllabus is the next to the last item, and then I also have a folder of lecture PowerPoints. Okay, I'm going to store these on Canvas. They'll be modified and uploaded to Top Hat, which I'll talk about shortly. Yes. Yeah, that'll work better. Okay. So here's the syllabus. Okay, so my name is Dr. Trump. I graduated from Salina Central High School, went on to Doane College, and then I went to graduate school at Kansas State University. And then after graduating from Kansas State with my PhD, I went to work right away at Emporia State. So I've spent my entire academic career here at Emporia State. My specialization is organic chemistry. I've done research in the area of medicinal chemistry, developing compounds of potential therapeutic value, including anti-cancer and antimicrobial, and then I've done some research on COPD, chronic obstructive pulmonary disease. I have an interest in radioactivity. I spent a sabbatical at Lawrence Berkeley Laboratory in California. My current project is to determine what makes opossum fur fluoresce. We're trying to identify the compounds that are present in that. Fluorescence in mammals is actually very rare. There's only very few mammals that have that property. Okay, I have office hours Monday, Wednesday, Friday, 10 to 12. Also by appointment. We could do that. We could do that in the next room or online. Okay, so if you do have questions, be sure to communicate with me. Okay, the required text are Organic Chemistry by L.G. Wade, 9th edition. And this comes bundled with Mastering Chemistry. If you've got a used copy, there's some instructions on how to obtain Mastering Chemistry. This is different from the online program we used last year. There's also a workbook called Pushing Electrons. In the past, I've collected pushing electrons. This year, I'm going to make assignments, have you work the questions, and then I'll give you a quiz after the due date. Pushing electrons teaches you some very important skills that you're going to be using all year long. It doesn't matter to me if you get the print or the ebook. Okay, so as I mentioned, Mastering Chemistry is that's the one that Pearson puts out. It's bundled with the Wade textbook. Good news with all of this is if you take Organic Chemistry 2, you won't have to buy any books. We'll use, except for Pushing Electrons, we'll use all of these again next semester. Same way with lab. We're going to use the same lab textbooks next semester. Okay. Yeah, I'll send you email messages regularly. So be sure to check your email often. The grading scale is a straight percentage based on the number of points you earn versus the number of points possible. Grading will be based on homework, quizzes, our exams, and final exam. I may not give the standardized final exam yet, since you'll be learning remotely at that time. So you'll have an exam, but maybe not that one. Okay, I don't give extra credit. Okay, this is the academic dishonesty policy. Okay, all students at ESU are responsible for knowing the academic dishonesty policy of this institution. Academic dishonesty in any portion of the academic work will not be tolerated. Academic dishonesty, a basis for disciplinary action, includes but is not limited to activities such as cheating and plagiarism. And then it talks about the possible penalties for academic dishonesty. So generally a 0 is assigned to the assignment exam if there's any cheating or copying of any kind. On the second violation, I can remove you from the course. Okay, student accommodations. So Emporia State will make reasonable accommodations for persons with documented disabilities. Okay, if you have a disability which requires accommodation, you need to talk to the Director of Student Accessibility and Support Services, and they will contact me about what accommodations are needed. Okay, and all of that will be strictly confidential. Faculty-initiated student withdrawal. Okay, I can withdraw you from the course, and there are two main reasons. One is excessive absences, and the other is disrupting the course. Inclusivity and diversity. Let's say I support both of those. Emporia State University supports an inclusive learning environment where diversity and individual differences are understood, respected, appreciated, and recognized as a source of strength. We expect that students and faculty at Emporia State will respect differences and demonstrate diligence in understanding how identities, perspectives, behaviors, and worldviews may be different from their own. If there are aspects of this course that result in barriers to your inclusion or the inclusion of those around you, contact the individual with whom you are most comfortable, whether that's your academic advisor, department chair, school or college dean, dean of students, chief diversity officer, or your course instructor. Free tutoring will be offered through ACES. I believe they are offering in-person tutoring, maybe by appointment, but I'll get the details on that. I'm not sure what the schedule is yet, but I know they will have tutoring through ACES. I know over the summer it was all online. I think maybe they're doing some in-person. Okay, these are the overall learning objectives. Okay, one of the things that you'll be learning is the system of nomenclature for organic compounds. We'll use structure to predict physical properties, know the major functional groups, and we'll define that shortly, what that means. That's a particular group of atoms that occurs in a molecule on a regular basis. Number 4, to understand organic stereochemistry, that's the 3-dimensional geometry. And then number 5, this overlaps with lab, but we will talk about spectroscopic data using certain instrumental methods to deduce the structure and identity of organic compounds. Okay, we will cover the entire book this year, and we'll cover roughly half of the textbook the first semester. Okay, so these are the topics that we'll be covering. Okay, so here is the course calendar. Okay, let's see, I may need to correct that. I think Labor Day is the 7th. Let me check that. Okay. Okay, but anyway, we won't have class on Labor Day. First exam, second exam, and I'll decide on the details of how I'm going to give those exams. The full enrollment exceeds the room capacity, so we'll probably have to somehow do those online. Okay, we have another holiday coming up in November, Veterans Day. We'll have a week off for Thanksgiving, as do all classes. And the last week, classes will be delivered remotely. And then the third exam is Friday, December 4th, which is the last day of class. And then final exam is scheduled for December 9th. Okay, you can access Mastering Chemistry through this menu item called My Lab and Mastering. This is the instructor view. Your view might look a little bit different, but there's a menu item called Mastering, My Lab and Mastering. Okay, and this is where you'll find online assignments. Okay, I haven't made any assignments yet, and I will, I'll notify you when assignments are posted. Yeah.
When will they start? Because I went to the bookstore today and they're sold out of all the books. All that chemistry stuff, like for organic. We didn't have any textbooks to do. So I don't have the
Oh,
access code.
okay. Let's see, the first mastery chemistry is probably, I haven't assigned anything yet, but probably toward the end of the week. And I have, I think I have an older edition of the textbook if you want to borrow that. I've got a couple different editions. Okay, any other questions? Okay, so that's where you get to mastering chemistry. So we'll go back here. And oh, one other thing that I didn't mention on the syllabus, and that is you should have received an invitation for what's called Top Hat. Okay, make sure that you respond to that quickly. In the next few days, we're going to be using that. That's a clicker program. Yeah.
What's it called?
Top Hat.
Top Hat.
Yeah. You should have gotten an email. If you didn't, let me know. I can send you another invitation. And that invitation didn't come from me. It would have come from Top Hat. Okay, so let me know if you don't get that. I'm going to go ahead and open this up and then pause it for just a minute here. Upload. Looks like I'm not signed up for Microsoft Office, but I'll check. I can still do the PowerPoint. Okay. Let me go back to Zoom here. And share the screen. See if I can zoom in here. Oh, here we go. Okay. Well, this is organic chemistry. What is organic chemistry? It's not the same as biochemistry. Biochemistry is the study of chemical reactions that occur in living systems. It turns out that biochemistry does involve a lot of organic compounds, though. Organic chemistry is the chemistry of carbon. Carbon is unique in a number of ways. Okay, so why does one branch of chemistry involve just one element in its compounds? Well, it turns out that about 97% of all chemical compounds known are organic compounds, compounds of carbon. The term organic is a historical artifact. Organic compounds don't necessarily have to come from living organisms. Back in the 1700s and early 1800s, we had what was called the vital force theory. And according to the vital force theory, it was believed that organic compounds had to come from plants or animals. This was actually disproven in 1828 by a German chemist named Friedrich Wöhler. And Wöhler made urea. And he did so by taking this compound called ammonium cyanate, heating it, and he obtained urea. Okay, so this was the first organic compound produced in the laboratory. Urea is a compound that is a waste product of animal metabolism, and he produced it without an animal's kidney, and this was identical to what was isolated from nature. Okay, since then, many organic compounds have been prepared in the laboratory. Some identical with those that occur in nature, some not. There are about 10 million organic compounds that are known, and about 1,000 are discovered every day. Carbon has very unique properties. This is an example of an organic carbon compound. This is the stuff that clogs up your arteries. Cholesterol. Black represents carbon. Red represents oxygen. White is hydrogen. And okay, we've got carbons that are in chains. We've got, okay, you probably see there's some that are in rings. Most of the bonds are single bonds, but right here, we have a carbon-carbon double bond. And this carbon skeleton is fairly strong, and that allows us to build compounds such as this. In the original Star Trek, there was a creature called the Horta, and the Horta had its biological molecules based on silicon. Okay, so the writers probably had some understanding of periodic properties because silicon is right below carbon, and we know that elements that are in the same column have similar chemical properties. Problem though is that while we can have chains of carbon that are thousands of atoms long, make something like polyethylene, okay, which may be many thousands of carbon atoms long. The limit to silicon chains is about 10 silicons. After that, the chains get too fragile. Okay, another difference is that here we have a carbon-carbon double bond. We've got a carbon-oxygen double bond in urea. As far as we know, silicon doesn't form double bonds or triple bonds with itself. Okay, so these are unknown. Okay, what about, okay, if silicon chains are fragile, what about mixing up silicon and oxygen, a silicate? Okay, one example here, this is quartz. Quartz has a tetrahedral geometry of silicon, and every silicon is bonded to 4 oxygens. And this network goes on and on in 3 dimensions. So this is a single molecule of silicon. Okay, and the bonds are very strong. Quartz is a very hard mineral. The quartz is also very unreactive. It's very chemically stable. There's not much you can do with that. So carbon has the strength of its skeleton, but it also has some reactive sites. Okay, such as this oxygen. Okay, such as this double bond. Okay, where transformations can be made, both in vivo and in the laboratory. Okay, and these are just some of the reasons that carbon is suitable for these types of molecules. Let me go back to sharing the screen if I can. Okay, so here we have a photograph of a firefly, and one of the compounds that's involved in the luminescent reaction is something called luciferin, and that's the structure of luciferin, and we can see that carbon not only forms bonds with itself, but it also bonds with a variety of other elements such as oxygen, sulfur, nitrogen. It forms double and single bonds as well as triple bonds, which are not shown here. Okay, and then here is a sample of 3 of the more than 10 million organic compounds that are known. This is one of the penicillin antibiotics. We'll be talking about that, its structure and properties the second semester. Taxol, an anti-cancer compound. Codeine, a narcotic. Okay, then we're going to review the structure of the atom. And we'll talk about various topics, but chapter 1 is mostly a review of first year chemistry. Okay, an atom has a dense, positively charged nucleus surrounded by a cloud of electrons. And electron density is greatest when the electrons are closest to the nucleus and falls off rapidly as the electrons get farther away. Okay, density decreases exponentially. The atom is mostly empty space. Depending on the particular atom, the atomic diameter may be 100,000 or so times greater than the diameter of the nucleus. An example that's been used is and this will vary with the element, of course, but for some generic atom, if the nucleus is the size of a tennis ball, the atom is the size of a professional sports stadium. Okay, so this is actually a, let's see, backing up one. This is a 1s electron. And for a 1s electron, density is greatest when it's closest to the nucleus. 1s electron has a spherical shape. And the reason that this is fuzzy is that a 1s is an orbital and not an orbit. Okay, the difference is that an orbit has a well-defined trajectory. Okay, the planets and the celestial bodies travel in orbits. Okay, and we can predict where Mars is going to be at some time in the future, even decades into the future, we can predict where it's going to be based on its orbit. Okay, but because of the Heisenberg uncertainty principle, we cannot know the position and momentum of an electron at the same time. So this is a probability map. So this is a region of probability of finding the electron. And we can define a certain probability, 90% or 99%, a certain probability of finding that electron. Okay, on the next slide, we have a 2s electron orbital, and it is also spherical. Again, it has a lot of density near the nucleus, but then it also has something called a node, and this is a spherical node. Okay, so if you think of an onion has layers. There's a core, and then think of an empty area, and then another layer. Okay, that would be what the 2s electron orbital is like. The 3s would have two spherical nodes. So there's a region of high density, a region of almost zero density, and then another region of high density. Okay, so this is in 3 dimensions, cut away. Okay, this is not circular, but it's actually spherical. In this course, although there are s, p, d, and f atomic orbitals, first semester we're just going to talk about s and p orbitals. The second semester we will we'll briefly talk about d orbitals, but mostly s and p. Okay. So going in this order, we fill up the 1s, and that's the first row of the periodic table, hydrogen and helium. That atomic orbital can only hold 2 electrons. Once it's filled, then we fill up the 2s, which is lithium and beryllium, elements 3 and 4. And once that's filled, we begin filling up the 2p orbitals. There's only one 1s and only one 2s, but there are 3 2p orbitals. These are all what we call degenerate, which means they have the same energy. They have the same size, and they have the same shape. But how do they differ from each other? Okay, there's a clue down here in the lower right corner. And that is the direction in which they're pointed in space. And it's very convenient to align these along an XYZ coordinate system. They're 90 degrees apart from each other. One is oriented along the x-axis, one along the y, one along the z. Unlike the 2s and the 3s and other s orbitals, the 2p does not have spherical nodes. Instead, it has a planar node. And so that nodal plane actually runs right through the nucleus. And so there's almost 0 probability of finding the electron at the nucleus in a 2p orbital. Okay, so the density increases, it reaches a maximum, and then it drops off with increasing distance. So the 2p orbitals have a dumbbell or figure 8 shape. And again, this is shown as fuzzy because this is a probability map. Okay, we will be talking some about isotopes later on in lab. There's a spectroscopic technique in which isotopes provide very useful information. Isotopes are defined as atoms with the same number of protons but different number of neutrons. So they have the same atomic number but a different mass number. Mass number is the sum of the protons and neutrons. Okay, so carbon-12 would have 6 protons and 6 neutrons. Carbon-14 would have 6 protons and 8 neutrons. Isotopes are useful experimentally in a number of ways. They can be used as tracers. If we examine a product mixture, okay, which product compounds have the isotope labeled atoms present and which ones don't. Okay, that's just one example. Isotope abundances in nature are also useful in mass spectrometry and identifying certain elements. Okay, here is the electronic configuration of the first 10 atoms, first 10 elements. And the valence electrons are the ones that are outermost, and these are the ones that most affect the chemical reactivity. Elements are arranged in the periodic table by columns, and each column represents elements that have the same number of valence electrons. And with the same number of valence electrons, that gives these elements in families similar chemical properties. Okay, so this is what I was saying before. Okay, we fill up the 1s. Okay, with helium, that's at the end of a row. Helium has 2 valence electrons, and then we start filling up the 2s, and then the 2p. There are 3 2p orbitals, and so with boron, which comes right after beryllium, it doesn't matter which one of the 3 we put that electron in. Arbitrarily, we put it in the x. Okay, the p orbital aligned along the x-axis. With carbon, okay, the next p orbital actually accepts. The next electron actually goes into a different p orbital because electrons in different p orbitals do a better job of avoiding each other. Electrons repel each other, and on average, they're farther apart. Nitrogen has 3 unpaired electrons, 3 p orbitals, and 3 electrons in 3 different p orbitals. But then when we get to oxygen, one of those has to be doubly occupied. Okay, arbitrarily, we'll put it in the x. And then when we get to neon, neon's at the end of a row. Okay, and all of the p orbitals are filled. Okay, so the column on the far right of the periodic table is the noble gases. And in terms of electron configuration, what they have in common is that all of the p orbitals are filled. What they have in common chemically is that they are all very unreactive. They're called the noble gases. And at one time they were called the inert gases because it was believed that they could not form compounds. But then in the early 1960s, compounds of xenon and krypton, krypton's element number 36, xenon is 54, were prepared. And it is believed that there's a compound of argon. This is that's been identified, but it is only stable at extremely cold temperatures. But there are no compounds of helium or neon that are known. Okay, so very unreactive. Those elements that are either one before or one after noble gases are the most reactive families of elements in the periodic table. Namely the halogens, either one electron short of a noble gas, fluorine, chlorine, bromine, iodine, and the alkali metals, which have one outer electron, one valence electron. So they have a noble gas core plus one electron. Okay, those are the 2 most reactive families. Okay, so Aufbau principle simply says that we fill the lowest energy orbitals first. Each orbital can hold a maximum of 2 electrons. Hund's rule says that when we're filling, for example, the p orbitals, we place one electron in one p orbital, the second one goes in a different p orbital, the third one goes in a different p orbital. And they'll have the same spin pairing. Okay, so electrons in the same atomic orbital will have opposite spins. All right. So to obtain a noble gas configuration that is a full valence shell, all of the p orbitals filled. There's two ways we can do this, by transferring electrons and by sharing electrons. We're going to talk about transferring electrons first. Okay, if electrons are transferred from one atom to another, then the atoms will now bear opposite charges and they'll attract each other, forming an ionic bond. Okay, so a lithium atom has one valence electron. Electrons have a negative charge. Okay, so there was a lithium atom walking down the street and he said, I lost an electron. And another lithium atom said, are you sure? I'm positive. Okay, so when lithium loses an electron, it becomes positive. A fluorine atom has 7 valence electrons, and it's very reactive, and so when it gains an electron, it has one more electron than it does protons, so it has 10 electrons and 9 protons, and so it carries a negative charge. Okay, these oppositely charged ions attract each other and form an ionic bond. Okay, I will have more to say about ionic bonding and covalent bonding next time. And I'm going to go ahead and end the meeting. So no homework has been assigned yet, except do go ahead and read through chapter 1 of the text. Okay, I will see you next week.
So Friday, Saturday,